Hi again! The last preparation task we are addressing is data balancing. The need of balancing occurs in the context of classification, where we aim for creating a model able to predict the value taken by some particular variable of interest, usually known as class or target variable. In order to create those models, machine learning algorithms take a set of pre-classified records and use them to train the model. The problem arises when this dataset is unbalanced. Datasets are said to be unbalanced when the number of records for one of the classes is much higher than for the others, which translates into having a target variable with a highly skewed distribution. The problem with class imbalances is that machine learners are often biased towards the majority class, since these classifiers attempt to reduce the error rate, not taking the data distribution into consideration. As a result, records from the overwhelming class are well classified, whereas records from the minority class tend to be ignored and consequently misclassified. Unbalanced data is an intrinsic characteristic of some domains, such as fraud detection in any context, since the number of fraud situations is a very small fraction of the stored ones. Diseases diagnosis, not necessarily rare diseases, because fortunately there is more healthy than sick people, false detection where machine faults are described, and natural disasters such as earthquakes, nuclear explosions, floods, to name a few. To address this situation, there are two main approaches: weighing and resampling. Usually, each record in a dataset has the same importance as others, and so, when machine learning algorithms look for the right predictor model, they tend to give the same importance to all of them, which means that they just try to minimize the number of misclassified records. In reweighting, the idea is just to give more importance to records from the minority class, in a manner that the weighted sum of the records in the different classes tends to be equal. Naturally, the easiest way to weight a dataset is just to assign to each record 1 over the number of records in its class, but this can be extended to take domain expertise in consideration. In our example, the green points would be valued 1 over 6 and the orange ones 1 over 3 each. On the other side, the idea behind resampling is to change the data distribution, balancing the number of records in the different classes, changing it to a uniform distribution. The result of the resampling operation will be a new dataset where there is approximately the same number of records per each class. There are two major approaches to resampling: by undersampling, by keeping the entire subset of the minority class and joining it to a subsample of the majority one, or by oversampling, keeping all the data but enlarging the number of minority records to the same number of records in the majority class. This enlargement is done by replicating the minority records as many times as needed. Naturally, we can also think of a mixed approach, taking all the minority records, enlarging their sample to a chosen size, and taking a sample from the majority class with the same amount of records. An alternative to oversampling by replication is to create a synthetic set of objects that are expected to belong to the majority class. This technique is known as SMOTE, standing for Synthetic Minority Oversampling Technique. It usually combines the oversampling of the minority class with the undersampling of the majority one. So, given a chosen number k, for each one of the minority records, we'll look for its k nearest neighbors from the same class and create an object in the middle of them. Here, we illustrate the process with one neighbor and create 3 new objects expected to be orange. It is important to note that SMOTE adds some risk of error since there is no guarantee that the new objects belong to the minority class. The approach is riskier when the separation among the records on both classes is not clear. Indeed, when there is a majority record between pairs of minority ones, the probability of the new object being misclassified as the minority is even higher. With these approaches, balancing the data is easy enough, but each one of them faces some challenges. With respect to undersampling, we need to grant that we take a representative subsample of the majority class, not ignoring any portion of its space, and it should be used in the presence of very large, dense datasets, where the majority class spans along with the space. On the other hand, oversampling by replication shall be applied when, despite being few, minority records widely cover the region expected to represent the minority class, while SMOTE should be applied when minority samples are too similar and we need to enlarge the space covered. It is important to note that changing the class distribution makes the learners more biased to the minority class, which implies the need for special attention to the assessment of the results. Now that we have addressed the most important transformation techniques, we hope that you are able to use them whenever you will need them. Bye-bye!